So welcome to the Chapter 20 pre-lecture video introducing you to the t-test. Well, I figured that after years of hearing Ellen Fireman talk about how influential the Stat 100 team is and how wonderful her lectures are and how they just stay with the students for life, that she is just a teacher for life, and once you learn statistics in Stat 100 you never forget it. I just have a question for you.
Well, you're an example of that.
It's true. I was a student and I've never forgotten it.
I know.
Well, I have a question. If we, say, took students from 2 years ago, from Stat 100, who haven't had statistics experience since Stat 100, if we randomly selected some students from 2 years ago and had them sit for a Stat 100 final today, or this week, what do you think they would get on average on the
Well, I think if we actually had the whole class, and we said, okay, we advertised it, we said, all right, class, let's see what you remember. You know, if it was a university, if we could have the university do this, have, you know, them do it for a lot of classes. Don't you think it would be a good idea, see what people retain?
Yeah.
So before they go, so they give my students a Stat 100 exam, and I think they do fairly well. I mean, not as well as in the beginning, but, but I'd say 80.
An 80% average. Okay, well, Ellen, I have to tell you, I designed an experiment to test this theory as you have of your students doing so well 2 years later, and I randomly selected from the pool of students who took Stat 100 2 years ago, I randomly selected 9. Only 9. I know it's a small sample, but I figured having students sit for a 3-hour final, I didn't want to be cruel and use a sample size of a couple hundred. So I randomly selected 9 students. I had them sit for the Stat 100 final exam 2 years after taking the class, and the results might be disappointing to you. The average was only a 72 compared to your expectation of an 80. So I think that that's kind of a really large difference, and...
Well, wait a sec. It might not be. I mean, 72, 80, that's only an 8-point difference. You know, there were only, what, 9 students? Just by the luck of the draw, you could have picked some of the worst students, Jackie.
Oh boy, or some of the best, so
That's
we don't
true.
know.
So I think what we need to do, we really can't tell if that's a big or small difference. We can't really tell unless we set up a significance test.
Great.
So let's do that.
Yeah.
So let's pretend we did what I'd like to do and have every single Stat 100 student, all 1,100 of them, come back and sit down and take the exam. So our box model would be 1,100 tickets. On each ticket would be written an exam score.
Yeah.
And I think that the average would be at least 80. I don't know what the standard deviation would be. And I think usually the final we have more of a normal distribution. So it would be somewhat normally distributed in here. So the null hypothesis is, that's kind of the one I believe, is that the average of the box is at least 80. And this 8-point difference, this 8-point drop you see between what I think and what we actually got, what we actually observed, is small, just due to the luck of the draw, Jackie.
Well, I'm a believer in the alternative hypothesis, which states that this negative 8-point difference, that, you know, the 80 or the 72 minus 80 difference, is really large. I mean, that's a C, a low C, and that's a B. That's a pretty big difference. So I believe that the average of this box, the true average of this population of 1,100 tickets, which you claim to be 80, I claim it has to be much lower.
Okay, well, we know what to do. We got to do a significance test.
Let's go to the t-test.
Yeah, we're going to the t-test instead of the z because we have small sample sizes. Because of this, 9 students. When you have a small sample size and you don't know the standard deviation of the box, our sample SD is not a great estimate of it. It's going to be a little bit too low. So we have to adjust it. And basically, the rule that we're going to use here is that when we have a small sample size, about less than 25, and the data inside the box the population data is approximately normally distributed.
Or close to normal.
Close to normal. It's not, doesn't have, that's, close to normal is fine. And this is key. This is really key, that you don't know the standard deviation of the population. And your standard deviation of your samples is a poor estimate for it. It's an underestimate. So we have to make that a little bit bigger. Then we're going to use a t-test. So let's start and see. Let's see how it works.
Okay.
Let's see who's right. Students out there, you want to guess? How many of you wouldn't win? Lee, what do you think? Do you think?
Cast your vote now.
Cast your vote now.
Null or alternative?
Do you think the average of the box, if all the students took it, do you think that it could be, do you think it's 80 or higher is a good guess?
I think 80 or higher is a good estimate, yeah.
I mean, look at you. You took it 2 years ago.
Yeah, I'm doing great.
And Raquel, what do you think? Do you think that if you took the exam now, the final, you did really well? How many years ago was it, though?
Yes.
Do you think, judging on your experience, do you think you'd score at least an 80?
I don't know. Might have to go with the other hypothesis.
Oh boy.
Okay, so we
So
got
we're
a split. We got a split decision here. All right, so we got to figure this out. So we're going to do what's called the t-test. Compute a t-statistic instead of a z. And it looks very much the same. We're going to say the observed minus the expected. And in this case, we're talking about what?
Well, the test averages.
Averages. So the observed average minus the expected average over some kind of standard error. And since we're talking about averages, it's going to be the standard error for the average.
Great.
Well, the numerator, we know the numerator, the observed is 72, and the expected
That's
is
your
80.
claim. Right.
Yeah, so we know this is the 8-point difference we're talking about. But we have to figure out the standard error for the average. Does anybody remember what that is? What is this? Let's figure this out. What is the standard error for the average? Does any
Yeah.
SE? It's like an SD.
Divided.
Yeah, do you multiply or divide by the square root of n? Do you remember out there, students?
Divide.
Definitely
Good.
divide. Make it
See, and she
smaller.
remembers from 2 years ago. This is a good sign. This is a good sign. Square root of n. All right, but this formula really applies to the standard deviation of the box.
I don't
And
know
as
that.
I said, we can't use this estimate without adjusting it.
Yeah.
So we use something called SD plus to make it a little bigger. And what SD plus is, I'm going to write it right here. Instead of using this 10, we're going to say SD plus, and it's equal to the square root of, that's the square root sign there, square root of n divided by n minus 1 times 10. Notice this is always going to be slightly bigger than 1. And as n grows, it's going to become very, very close to 1. If it's, square root of 100 over 99, it's going to be really close to 1, whereas the square root of 2 over 1 will be 1.4. So, with our sample,
Well, we had a
size.
sample size of 9.
okay, so we can do that. And with a sample size of 9, what do we get here?
So that'll be
9 over 8 times 10. So it's a little bit bigger than 10. Is it 10.6 about?
Yep, 10.6.
10.6. So that's what goes right in here. So we have 10.6 over the square root of, now what's n? What's our sample size?
9.
Oh, good. At least you picked a nice one that has
Yeah.
a nice square root,
That has
Jackie.
some logic there.
Okay, so that's 10.6 over 3, and could somebody do that for me?
Let's see. You get 3.35.
That sounds right.
3.35.
So that's
our standard error for the average, and that's what we're going to plug right in here. 3.35. Does that look right?
That looks good to me.
All right, so now we just have to say, finish this up. And finally, we're going to get our t-statistic as what? negative 8 divided by
3.3.
3.35, which is equal to negative.
2.39.
Okay, so now that we've got this t statistic, negative 2.39, we have to see where it is on the t distribution. But the problem with the t as opposed to the z is there's a series of curves. There's not just one curve. There's one curve for each, a different curve for each sample size, depending on its degree of freedom. So what is a degree of freedom? Well, the degree of freedom, well, abbreviated DF, is just the sample size minus 1. So in this case, Jackie, what was our sample size? It was
9.
9. So we have 9 minus 1 equals 8 degrees of freedom. So, want to take it from there,
Yeah,
Sean?
now we're going to introduce you to the student t-table, which is just a little bit different from that normal table that we've been using in the past, in that this curve changes in its height, basically, with each different sample size you use. So depending on your sample size, you're going to need a different t-table. And that's why we use the degrees of freedom. So we calculated our degrees of freedom as being 9 minus 1, your n minus 1. So 9 minus 1 gets us 8. So we go down the table until we reach our degrees of freedom of 8. So this is the row that we want to look into. So then we are going to go across the row until we hit our t statistic. So I'm at 8 degrees of freedom, and I go across the row. There's 0.7, 1.4, 1.8, 2.3. I'm getting close, because our t statistic was negative 2.39. Then 2.9, that's too far. So I know that my t statistic falls somewhere between 2.31 and 2.9. So when I go up to the top row, which is the p-values, I know that my p-value is going to lie somewhere between 2.5 and 1%. So probably closer to this 2.5 value. So we can conclude that our p-value is just shy of 2.5 for having this 8-point difference between our observed and expected. So what does this p-value mean, Ellen, of being just shy of 2.5?
Oh, darn, we're going to have to reject the null.
It's underneath that, it's below that 5% cutoff, which means that this difference is just too large to be just due to random chance.
Yeah, if you want to think about it, it's like, what it means is this 2 point is about 2 point, will actually be over here. The negative, we have a negative, but you know that doesn't matter because it's symmetrical. So really we'd expect 80 in the middle, or 0, and we got 72. And we were just wondering how unlikely that is. And we find out that is it past a shadow of a doubt? It's way out here. So the probability that we would get a score of 72 or lower if the true value of everybody taking the exam is 80, if I was right, in other words, that probability is pretty small, and I'd say it's only 2.39%. No, it's only 2 point less than
2.5.
less than
2%.
Let's say it's about 2%. So there's only a 2% chance that if I was right, we'd see a random draw of 9 people getting as low as 72. So I guess we're going to have to reject the null, and I'm
We
not
reject the null hypothesis.
darn. But
I still think it's a pretty exceptional score.
72. Yeah, at least I should be happy with that. But
Absolutely. So good luck practicing the t-test, and we'll see you in lecture.